Today I would like to test some of the ideas that I described yesterday. The first point is this. To test those ideas, we need to have a good data set. So for example, in 2 dimensions, I would like to have a set of points like this, so that they have a particular trend that can be analyzed by the code. And in general, this is the case, of course, of 2 dimensions where data tend to be aligned along 1 dimension. How can we generate this? The idea is that, well, suppose that we want to generate points along this line. To generate points along a line, you can simply generate one random number, for example, random in -1, 1. Then, to create the 2 coordinates, let's call the x1 and x2 of that point, you just need the 2 coefficients, call them alpha 1 and alpha 2, so that x1 is equal to alpha 1 r and x2 is equal to alpha 2 r. If you keep alpha 1 and alpha 2 fixed and you generate different random numbers, what you get is a set of points that are aligned on a line where the slope of the line is alpha 2 divided by alpha 1. Okay, so if you generate many values of this random point, of this random value, you get points along this line. How do you generate the cloud? You add a small error to the point. Of course, this is valid in 1 dimension. So if you want to generate points that have 1 main dimension and you want to put them in a 2-dimensional space. In general, so remember that we want to have points in an n-dimensional space, but we also want that our cloud of points does not take complete advantage of all the dimensions. So let's call, I don't know, n0 less than n, the actual number of dimensions of the cloud. In this case, for example, we had n0 equal to 1, in the sense that the points would stay on a line, and n equal to 2 because we are in a 2-dimensional space. So we just need to generalize these this formula. We need many more coefficients, and in particular, so we need to generate a vector of random numbers let's say always in -1, 1, power n0. This will be the parameters. In this case, we only had one parameter r because all points had to be in a line. Here we need to have n0 parameters because we want our point to be on a n0 dimensional plane. Next, let's say that for I in one n, because we want to generate n coordinates, we need to have, okay, xi will be equal to, I simply generalize this for many, for n0 coordinates, so j from 1 to n0, alpha ij r j. Where alpha ij are fixed coefficients that determine how our cloud of points how the trend of our cloud point is with respect to the n dimensions. So here we are generating a set of we are generating points that occupy an n0 dimensional cloud in the n dimensional space. So alpha ij is set at the beginning, and I simply repeat this m times to have m different points. This equation places points exactly on the linear subspace, so I just add a new random number, a small random number in, for example, minus 0.1 to 0.1 here in order to slightly disperse the points. This should do the trick. Okay, if we generate points like this, we will have precisely a situation where we have n coordinates, but not all n coordinates are needed in order to describe our system. Actually, the system lives in an n0 dimensional subspace with some noise, which is this error. Once we have created this data set, we can try to analyze it with the principal component analysis technique that we have seen yesterday. So, first of all, let's try to create these points. So basically, the idea is that I want to create points in n dimensions, but I want them to depend only on a smaller set of parameters, n0 parameters, so that the points are forced to stay on a slice of this space. So let's see. Suppose that I want to create, let's call it cloud.py. Okay. The idea is that the first thing I want to let's say I want to generate my points that I call the x, but since it's easy with Python to create matrices by rows, actually I'm going to create a matrix X transpose, where the first row will be the coordinates of the first data point. Remember that the number of coordinates is n up to m points. xm1, xm, n. Okay, so I will call the matrix xt because it's different. It's transposed with respect to the matrix that I showed yesterday. To generate this, the steps will be: first, create the coefficients alpha ij, which will be needed for the rest of the data set to be created. Alpha ij are coefficients where I is the coordinate in the n-dimensional space, and j is the coordinate, is the number of the parameter. So j varies from 1 to n0. Next, using these aij's, I will generate the ODXI points. So first of all, let's decide that, for example, let's define some constants. For example, in order to see things on the screen, I would like, for example, n0 to be 2, while n is 3. Okay, I want to embed a two-dimensional cloud of points in a three-dimensional space. But I also want to keep the code general enough to change it later. And maybe I want to generate 100 points. So let's call m, as usual, the number of points. Next, I need to generate the set of alpha parameters. Let's put them in a list of lists because it has two indices. So initially the list is empty. I need to generate how many rows? N rows for alpha. So the first and let's call A the row that we're going to generate. So initially empty. Well, no. Let's say that I append into alpha a row of random values. So I need, of course, here the random package. And we want to generate n0 random values between -1 and 1. It will be simply random dot uniform from -1.0 to 1.0 for a dummy variable j in the range from 0 to n0. This should generate a row, the list of n0 random numbers, and this is generated n times. Actually, if we really want to push list comprehension to the top, we can generate alpha as a list of lists for I in x range. And so we don't have loops, we only have a list of lists. Let's see if it works. Okay, so I have 3 rows of 2 parameters each. Okay, now that we have the parameters, I just repeat 1m times the generation of 1 point, and I put the results into an initially empty list. Every time I will generate n0 random values, which are my initial R parameters. So R will be a vector of just like this. N0 random values. The vector x will be filled up with n values, where the jth value, which starts from 0.0, is computed by adding the k parameter times alpha j k. So this for loops computes one coordinate of the dataset. Then I have to add also a small random noise to that coordinate. We said from -0.1, well, let's say minus noise to noise, where noise will be defined here in the parameters. And finally, I want to append xj to x. Until, at the end of this for loop, we have that x is a fully formed n-dimensional vector depending on n0 parameters. So I can append this vector to the matrix containing all the points. xt is a matrix, is a list containing 100 n-dimensional points that actually come from an n0 dimensional set of parameters. So let's output these parameters and see these points and see how they appear on screen. So let me simply write them. So for every point in xt, I want to write out, let me import the sys package. So sys.standard_output write. So I can write the values of x separated by spaces. Oh, just a moment. X, of course, are float numbers. So in order to join them, I need to convert them to strings. So I need to map the str function on x. Right. This. And of course, I want to end every line with a new line character. Okay, this should generate the list of three-dimensional points. Not really. I forgot something.
You have put xt append xt.
Oh, thank you. Actually, it's very interesting to see how Python is never afraid of doing things like that. Okay, now we have much more reasonable points. So let's say I can save them to a file. I don't know, points. Well, let's call points the file. And we can see them with the GNU plot. For example, we can, they are three-dimensional, so I can use the splot command to see all points. And in fact, you can see that they are in a three-dimensional space, but they form a noisy two-dimensional plane within the three-dimensional space. They are not evenly spaced in all the three-dimensional space. We could change the constants to see it better. For example, if I remove noise, I put noise to 0, then the points that I generate with the script will fall exactly on a plane. So if you look at them at the right angle, they will look aligned. They are actually on a two-dimensional structure within the three-dimensional space. And of course, let's go back to a little noise. I can also, by setting n0 to 1, we generate the points and look at them with GNU plot. Now all points are more or less on a one-dimensional line with noise in the three directions. So in this way, we can generate different data sets where not all coordinates are needed to describe the points. Of course, if we look at the points themselves, it's difficult to understand that they are on a one or two dimensional variety of manifold, on a one or two dimensional line or plane, because they actually occupy all the range at their disposal in all three dimensions. There is no one dimension that is clearly smaller than the others. So we cannot say by just looking at the data that they have this particular direction. So let's see how we can look at this. Okay, maybe I can keep this program to create the cloud and open another file that we can call pca.py, where we create, where we analyze this data set and okay, try to find the right set of coordinates to analyze it. So first of all, of course, I want to read the data file. So let's say now I created the file as a where every point is a line and every line is separated by spaces. So I can simply let's create a function that reads the points from an input file F. How can we read those points? Just start with let's call xt, okay, our data set. We start with an empty data set, and then for every line of our file F, we append to xt the set of floats that have been read from that line. So let's say we append float of let's call S the string for S in the line L once we have split according to the space separators. Okay. Okay, this should be it. Well, of course, even in this case, I can just write that xt is this set of lists for line in F, and instead of putting it on xt, I can simply return it. So this should work. So I just create xt as read points from this file, where of course the file must be open. Suppose that it's called points as a read-only file, and we close it at the end. Let's see if xt is read properly. So okay, this was line, don't split. Okay. Okay, so let's separate. So above there, I'm going to put all the functions that we need to analyze the points, and down I write all the rest. So here we have a second program that reads the output of the first and puts it in the xt matrix. Now, the first thing we want to do is, if you remember, we want to normalize the matrix so that every coordinate has 0 arithmetic mean. The arithmetic mean of every coordinate, so of every column of this matrix, which is the transpose of X, has arithmetic mean equal to 0. So I just define a function, let me call it normalize, which takes a matrix as input. Now for every column index, so J as a column index in sorry. Okay, here we need to know what the number of dimensions is and the number of elements. So M is the number of elements in xt, and N is the number of elements of every row in xt, for example, the first row. So I want to vary j along the columns n, and for every column I want to compute the mean, the arithmetic mean, so for every row I add xt of ij to the mean value. Finally, I divide the mean value by the number of elements. And now I repeat the same iteration, this time subtracting the mean from the value. So I have subtracted mu1 from every element in the first column, mu2 from the second, and mu_n uppercase n from the last. Now, our point data set is such that the origin is in the middle of it. So I call the function normalize here, and we are done. Okay, so we read the function, the data set, and we normalize it. Next, I need to compute the covariance matrix. The covariance matrix is the matrix of dot products along the coordinates. So the covariance matrix is a n by n matrix that tells us the covariance between two of the coordinates. So I need to compute the dot product of every pair of columns of matrix xt. So let's just define yet another yet another function, covariance, that takes as input the data matrix and returns the covariance matrix. So as usual, initially the covariance matrix is empty, and then for every row of the covariance matrix, let's call R the single row of the covariance matrix. I start with an empty row, and for J here I just add all the pairwise products of two columns of matrix xt. So for k in the dataset range, I add the product between the ith column and k here. And the jth column. Next, I want the mean, and I append this sum to the covariance matrix row, and after creating the row, I append the row to the covariance matrix, and finally I return the covariance matrix. Okay, it's the average of all the pairwise products between different columns of the matrix. So I can take the covariance of xt, put it into matrix cov. We can also print now the covariance matrix. Okay, oh, I forgot that n and m are not anymore global variables. So I just copy them where needed. Okay, this is the covariance matrix. What's important, you see that it's far from being diagonal. We would like, at the end, a diagonal covariance matrix. This is, well, definitely not diagonal. Everything, all numbers are different from 0 and also very different in some cases. Of course, always in the range -1, 1 because I generated small random numbers. Okay, so as you remember, the PCA method tries to find the frame of reference where the covariance matrix is diagonal. Let's see how. Okay. As you remember, what we need to do now, very simply, is find the principal eigenvector of the covariance matrix. So this is what I want to do. I have, let's write another function to find the principal eigenvector. So I simply define the function principal eigenvector. Let's write it for a generic matrix A. Of course, A will be, in general, our covariance matrix, but we will see. And if you remind, well, we start with a random vector, and we repeatedly multiply A by that vector, repeatedly normalizing it. That's all. So, we just need to repeat something for a certain number of steps. For example, for 100 steps. At every step, before repeating steps, of course, I need to generate the initial vector W, which, as always, will be a list of random uniform values in -1.0, 1.0. For I in, okay, actually it's the dimension of A. Okay, so we see how many rows A has. We assume that A is a square matrix, and we generate a vector of n random numbers. So, by the way, here, of course, I need to import the random package. Now, every time we take another vector, W1, let's say I will define another function product that, given a matrix and a vector, returns the product matrix times vector. Let's call, let's see, oh no, let's put it on W itself. Next, I need to compute the length of the vector W. Okay, let's call it length of W. And I need to, actually we already have a function called normalize, so I will call this divide W by L. Okay, I repeat this many times So every time I multiply A by the vector and I renormalize the vector given its length, finally I just return the final vector after 100 iterations. Actually, let me return also L, which is an approximation of the eigenvalue of the vector, because it is the last product, the next to last product between A and the eigenvector itself. But before testing this function, we need, of course, to define the product between a matrix and a vector. And of course, to do this, let's start from an empty list Y. Then for every, I need to generate let me put it also here. We know that A is square, so I just need one dimension. If you want to make it a bit more general also for non-square matrices, of course you need also to take the number of rows of the matrix, but not necessary in this case. Just keep a sum starting from 0, and for j in the range from 0 to n minus 1, I add to sum the product between A, I, J, and J. I append, sum is a reserved word. Let me call it S. Well, actually also sum worked. I think I already used it before. Okay, so actually it works. And I return Y. Okay, so we have a matrix by vector product. We also need to compute the length of a vector X. And we just start with an empty sum, a void sum, and for every value in X, we just add its square to S, and we return the square root of this, meaning that I also need to import the math package in order to return the square root of the sum. Okay, this will return the principal eigenvector. Oh no, I also need to divide the vector by its length. Well, this is easy. I want to divide a vector X by a generic scalar value A for I in the range of the length of X xi is divided by A. Okay. Of course, many of these definitions could be shortened by using functional properties. For example, here we can use a map to map this division, but it would be overkill. Okay, so after we have the covariance, we can take the principal eigenvector. If you remember well, we called it P. P1, P2, Pn were the eigenvectors, with lambda values L as the principal eigenvector of matrix, of the covariance matrix. Okay, now we have the first eigenvector, which is we have the direction along which the points are most spread. We want to iterate on the next eigenvectors, because I want to get a complete reference frame. So actually, I want to repeat various steps of this. How many times? Well, as many times as there are, for example, rows in the covariance matrix. I want as many times as there are dimensions in my dataset. So, for example, the number of rows in the covariance matrix. Every time, of course, after computing the principal eigenvector, I need to remove that eigenvector from my data points. So I need to remove the component of my data points along the direction of the eigenvector. So let's just say we have a function, remove yes, I want to remove from my dataset xt the projection of points along the direction p. And I want to do it on place in the xt matrix. So I define the remove projection function. Let's give the same name to the parameters so it's easier to remember what they are. Now, for every point x in xt, I want to modify the coordinates of x. To do this, I just need to compute the scalar product between the point x and the eigenvector p. Once I have this scalar product, I remove the projection of x along p. So I take the scalar product times p of I. Okay. So I have so I have my vector x. I have the eigenvector p. I'm going to remove this component of x in order to project x along this perpendicular direction. The perpendicular direction is precisely x minus x scalar p times p, which is what I'm doing here. Okay, everything has been done in place, so at the end xt will contain the new data set with one dimension removed. Of course, I need to define the function scalar product. Between two generic vector x and y. I simply define the usual zero sum, and for I in the number of elements of x, I assume that x and y have the same number of elements, I add the product between the ith component of x and the ith component of y, and finally return the sum. Okay, so I removed the projection. So now, here, I am, every time, computing the covariance of my data set, computing the principal eigenvector, removing the principal eigenvector. Of course, if I do this n times, what I get at the end is that my data points are, every time I remove one direction in xt, so all the points will be reduced to 0. But what I want to get here, in particular, okay, I want to store all the principal eigenvectors, all the eigenvectors, in one matrix. Remember, yesterday I defined the matrix V as the matrix having as columns the n eigenvectors. As usual, it will be easier to store the eigenvectors as rows. So what I'm maintaining here will be its transpose Vt. So start with the empty matrix Vt. Every time I compute a principal eigenvector, I append it to Vt. And let's also keep a vector L of the eigenvalues, uppercase L, where every time I append my new eigenvalue. Let's see what are the eigenvectors, and more important, let's see the eigenvalue that we compute in this way. Okay, I forgot something, line 88. All right. Here, the first time I haven't computed the covariance matrix yet, so this will be simply the length of one row of xt, okay? So the dimensionality of my space is the dimensionality of one of the rows of my data set. Let's see what other error. Okay, integer object is not iterable in line 58. Okay, here of course I need an iterator on n. Okay, so where I compute the principal eigenvector and I want to generate an initial random vector, I need to do it n times. Again, okay, here I put square brackets instead of round bracket, but random.uniform is a function. Okay, well, this is not what I was expecting. So first I have an error in line 53. This is length and not length. I hope you didn't copy exactly what I've done. Anyway, in the divide function where I divide a vector by a scalar, here I need the length function, which gives me the number of elements in a list. Okay, now you see what's happening. Look at the list of eigenvalues. What you can see from the list of eigenvalues is that the first is about 1/2. The others are much smaller, less than 100. This is 4,000 and this is 3,000 thousandths. So, in fact, this means that the system actually recognized that in the original data set there was one significant dimension, which is given by the value of the first eigenvalue, while the two remaining dimensions are much less important. Okay? If you remember yesterday, the magnitude of the eigenvalues was related to the actual size of the system, of the data set along that dimension. So, what this answer is telling us is that if we take the first eigenvector as the first axis of our new reference frame, the variance along that axis is 0.53. And as I told you yesterday, this is the largest variance we can hope to have in any direction. While the other directions that are perpendicular to it, because we are keeping a perpendicular reference frame, we should check that they are perpendicular, of course, have these very small residual variances. So, we have created a new reference frame where most variance of our points is captured by the first coordinate, while the others tend to work as noise in this case, because in fact we added small variations, small numbers, small noise contributions. Let's see what happens on a different data set. So let's go back to the point generator. Let's remain on 3 dimensions. This time I generate the points with 2 parameters. So here we have a data, now we're going to generate a data set where we need at least 2 dimensions to describe it well, while the third is just noise. So I generate again the points with by calling the first Python script. We can also check with gnuplot that the points are actually on a plane. So not really on a plane, but they are spread in two directions and they tend to align on a third. So they are distributed on a plane. This time, if we run pca.py, okay, here we have two significant values, 0.47 and 0.13. The next is much smaller, 0.002, 0.003. Okay, so in this case, the system recognized that there are two relevant dimensions and one which is not important. Okay, the next thing we can do is actually transform our initial set of points and rotate it according to these new coordinates, so that we actually take advantage of the new data set. So let's go back to the PCA function. Okay, of course, I need to keep in mind the original data set. So after normalizing it, I copy it into another list. So this is, I want to duplicate my matrix of data points xt and store it in a new matrix xt1, which I will use later. So I need to define the function duplicate that does that. It's easy. Well, let's do it in place. xt1 will be a list of vectors where every vector is let's say it's an xij for xij in xi for xi in xt. Okay, this should actually duplicate the structure of xt into another vector, into another list, xt1. Okay, now that we have now that we have stored a copy of xt that is not going to change here, well here I keep changing xt. Okay. Well, if you remember, what I want at the end is a new set of data, x prime, that I can compute as V transpose x. Okay, this is the coordinate change matrix that will change our original matrix x into a matrix where the n coordinates are independent of each other. So have mutual covariance equal to 0, which is what we want. How do I compute this? Well, actually, Actually, I prefer to compute X prime transpose because everything is transposed in our system, so it will be X transpose times D. So my new X transpose, so the final transformed data set will be the matrix product between the original X transpose matrix and the set of eigenvector which I have stored in V transpose. Of course, I need to consider the fact that V should not be transposed when I define the function. Let's define this function. So I need to define a matrix product between a data set which we call xt and actually the transpose of the second matrix Vt. So the result will be another matrix which I can simply call, okay, let's call it mu xt, initially empty. Then for every row in xt, I need to create a new row, let's call it y, by multiplying just a moment. So let's define n as the number of elements in the matrix Vt. I need to multiply that row of xt by each of the rows in Vt. So for every row of Vt, I just append to y the scalar product of just a moment. Is this the right transform? Or is it the opposite? So okay, yes, that's fine. So it should be the scalar product of x and p. And every time I compute a row, I just append it to the new xt, and finally I return new xt. Okay, here I might have misplaced some transposition, so I will need to check if it actually works. What I want to get here is, suppose we have this new data set, new xt. Well, no, let's keep. So let me just add some annotation to what is being printed. First, we are writing the eigenvectors of the covariance matrix. Next, we are writing the eigenvalues. Now, after I compute the matrix product, well, I could also print out the new data set, new xt. Well, let's do it. So this is the transformed data set. And we shall see what we can get from looking at the new data set. And finally, we can, of course, print the new covariance matrix. So just compute the covariance matrix of new xt with the covariance function. Okay, let's see how it is. Okay, let's start from the beginning. Now we have the set of points in 3 dimensions with 2 parameters, so that they were spread along the plane. So this was the result as before. 2 significant variances in 2 directions and 1 not significant. In fact, in the transformed data set, well, it's a bit difficult to see it because it's not printed in columns. Later we can change it. You will see that while the first and second coordinates have large variations, from -1 to 1, or from -0.5 to 0.5, the third coordinate will be systematically much smaller. Okay, we have found a rotation so that 2 coordinates are important, the third is much smaller. In fact, if you look at the covariance matrix, you see that we have achieved what we wanted. The covariance matrix is now diagonal, which is very important. You see, in the first row, the first element is high. It's actually the first eigenvalue that we have found, while the second and third values are negligible, 10 to the -16 and 10 to the -17. In the second row, we only have the central value important, while the others are 0. And also in the third row, we have the first two elements very small, 10 to the minus 17 and 10 to the minus 18, while here we have the residual variance along the third dimension. So we actually found a rotation of the axis, a transformation of the data set, so that the three coordinates are now independent of each other. We have removed all correlations between the variables, and we can, by looking at this data, we can actually decide that we don't want the third coordinate because it has a very limited variance. Okay, so this is precisely what I wanted to achieve. Now maybe we can we can write this a little better. So here, instead of printing so let's print the eigenvectors as a matrix. So here we can, for example, well, for P in Vt, we can simply print the eigenvector P like this. Also here for x in new xt, I print x. Also here for c in covariance, print c. So now at least all the vectors are in color. Okay. So you see, actually, the PCA technique is not that difficult. It's just a matter of, well, keeping in mind all transpositions. Let's see. Okay, the next thing I would like to do, and maybe also to put these programs together, is maybe make them parametric. So what I would like to do is, for example, cloud.py to take these parameters from the command line. So now if we don't have the right number of parameters, we can simply print the right syntax of the command. Which is cloud.py followed by parameters n0, n, m, and noise. And maybe also add okay, so now if I execute cloud.py, it tells me the syntax of the command. And here it generates the point. Okay. Second, I would like to do the same with PCA. Actually, PCA does not need any parameters to work. It only needs the list of points. Actually, what we can do here is transform PCA so that instead of opening an input file, we read it from the standard input, like this. So that now I can after doing the same here, so now I can pipe my generated points through the map. Of course, I forgot something. Okay, I need to make PCA.py executable, and now we have two commands where we can decide, for example, to test the procedure with in a 10-dimensional space with points that depend on 5 parameters. Of course, it's much more difficult to read everything because we have 10 dimensions now, but you should be able to see that in this case the covariance matrix is a 10 by 10 matrix where the first 5 elements in the diagonal are large, the other 5 elements in the diagonal are small, and here we have very small values. Of course, it's difficult to see it, and maybe we can format a little more. Anyway, now in in the next days I'm going to add a few comments on these two scripts and put them on the web page. So now, the next week is actually holiday, both Monday and Tuesday. Okay, Tuesday is the actual holiday, but Monday we don't have the university is closed. At least the academic calendar says so. So the next lesson will be on Monday, 8th of May, I think. Okay. So for today, I think that's all. If there are any questions, of course, I'll give them. Okay.